In this video, I want to show the moment generating functions for the binomial, geometric, and the Poisson distributions. And here are the moment generating functions. And then we can use the moment generating functions to find the expected value and also the variance. And so first, let's look at the moment generating function for the Poisson distribution. And so we say that x has a Poisson distribution if it has the following probability density function, f of x equal to lambda to the x times e to the negative lambda dividing by x factorial, where x takes on the values from 0, 1, 2, 3, 4, and so on. And then lambda is a positive quantity. The moment generating function is defined as expected value of e to the tx, which is the infinite sum of e to the tx times f of x, where f of x is the PDF here. And so in the place of f of x, we have lambda to the x times e to the negative lambda dividing by x factorial. This is e to the t times x, so I'm going to rewrite it as e to the t to the x. And then we can combine this term with lambda to the x right here. The summation here is with respect to x, so we can move e to the negative lambda and place it in front of the summation sign. And then e to the tx to the x times lambda to the x, which is lambda times e to the t to the x. Recall from calculus, we have the Taylor series for e to the x is the infinite sum from 0 to infinity of x to the k dividing by k factorial. So this is equal to e to the x, and so this infinite sum right here is going to equal to e to the lambda e to the t. And then multiplying this out, we get e to the lambda times e to the t minus 1. So this is the moment generating function for the Poisson distribution. And now let's take the first derivative and then take the second derivative. Evaluating the first derivative at t equal to 0, we get lambda. Evaluating the second derivative at t equal to 0, we get lambda plus lambda squared. The expected value of the random variable x with the Poisson distribution is the first derivative at 0, which is equal to lambda. The variance of x is going to be the second derivative at 0 minus the first derivative at 0 squared. And we also get lambda. And now we'll take a look at the moment generating function for the binomial distribution. And then from there we can figure out what the expected value and the variance of x are. So once again, we say that x has a binomial distribution if it has the following probability density function, f of x equal to n factorial dividing by x factorial times n minus k factorial, times p, which is the probability of success, to the x, times 1 minus p to the n minus x. And x takes on the values of 0, 1, 2, 3 to n. Recall that the binomial expansion for a plus b to the n is going to be this sum right here. And so instead of b, we have p times e to the t, and then instead of a, we have 1 minus p. Then this is going to equal to this is b, and this is a, which is 1 minus p plus p to the p times e to the t, and then the whole thing to the n. The moment generating function is defined as the expected value of e to the tx, which is the infinite sum of e to the tx times the PDF f of x. And for the binomial distribution, this is the PDF. Right here, I'm rewriting this as e to the t to the x. And then I'm going to combine this term with this term. So we get p e to the t to the x. And then now this sum right here, it looks like this. And so from the binomial expansion, we're going to get 1 minus p plus p e times e to the t to the n. And then I'll take the first derivative, and then take the second derivative, evaluate the first derivative at t equal to 0, then we get n times p. And then evaluating the second derivative at t equal to 0, then we get n times p plus n squared p squared minus n times p squared. The expected value of the random variable x is going to be the first derivative at t equal to 0, which is n times p. The variance of x is going to be the second derivative at t equal to 0 minus the first derivative at t equal to 0 squared. So this is the second derivative at t equal to 0, and then minus np squared. And we end up with n times p times 1 minus p. So this is for the binomial distribution. And now let's take a look at the geometric distribution. And so again, we said that x has a geometric distribution if it has the following PDF. F of x equal to p times 1 minus p to the x minus 1. Well, x takes on the values 1, 2, 3, 4, 5, and so on. The moment generating function is going to be expected value of e to the tx, which is the infinite sum from 1 to infinity of e to the tx times f of x. F of x is p times 1 minus p to the x minus 1. And then e to the tx is the same as e to the t, and then the whole thing to the x. And then what I'm going to do here is from this x, I'm going to subtract 1 and plus 1. So we're adding 0 here. And then rewrite this as e to the t to the first times e to the t to the x minus 1. And then we're doing it like this so we can combine these two terms right here, because they both have the same exponent of x minus 1. So this becomes p times e to the t, and then times e to the t, 1 minus p, and the whole thing to the x minus 1. And if we expand this infinite series out, it looks like this. And notice that this is a geometric series. The first term is p times e to the t. The common ratio is going to be e to the t times 1 minus p. And so from calculus, we have the sum of the geometric series is going to be the first term dividing by 1 minus the common ratio. And then take the first derivative, and we end up with this. And then take the second derivative, we end up with this. Evaluate the first derivative at t equal to 0, then we get 1 over p. And then to get the variance, first evaluate the second derivative at 0, and then we end up with this. And then minus the first derivative at t equal to 0, which is 1 minus p, or 1 over p squared. And then simplify, we get 1 minus p over p squared. And so in summary, this is the expected value and variance of the random variable that has a geometric distribution. And this is the end of the video.